So this is lab 4. We skip lab 3. This is lab 4. I want to number it as lab 4, and we're looking at really these are the graph basics. Specifically, you can see this main class that we're making is an undirected, unweighted graph. So this is like the most boring graph ever. All right, if this is the graph that would not get invited to parties because it's so vanilla. So we're starting with the simplest case. So remember what an undirected graph is. That's a graph where if A is connected to B, then B is connected to A. And it's unweighted, which means there's no number on the link. Okay? So really I need to start here at the node class. In this node class, I have defined a class node because I'm a computer scientist who studied networks. I don't think about them as vertices. I'm realizing now I should have probably called it a vertex class, but I call it a node. Can you go with me on this? So a node is a vertex. What is it that a node has? I want every node to have a string name. I want every node to have a list of its neighbors. So that's a list of nodes that are its neighbors. And I'm adding this one additional field or property, which I'm calling color. We haven't talked about color, I don't think, in this class. I'm taking this from this book, which I used to use for this class, which is a fun summary of graph algorithms. You can use color to represent whatever you want to, is kind of the beauty of it. So you could say it's a poor name, or you could say it's more versatile. We're going to use it to represent, like if we're doing a DFS search, a DFS traversal, have we visited this node yet? So we can use different colors to say white means unexplored, gray means we've discovered it, but we haven't fully explored all its paths, and black means we've fully explored it. Does that make sense? So you can literally end up, we've got 3 states that I'm representing generically as color. Does that make sense? If you really didn't like this approach, you could create individual fields that like is visited and use bools. Okay, so by default, I'm making every node white as its kind of baseline color before you do anything interesting to it. That's the little constructor here. You can pass in a name. If you don't pass in a name, it has a name of quote, quote. If you don't pass in a color, it gets color.white. And the list of neighbors is a new list of neighbors. So the list exists, it's just empty. It's just instantiating that list. So this is our kind of a utility helper here. This is a node. Okay, so what is a graph? A graph is a set of nodes. Well, it depends. How are we going to represent a graph? We have 3 possible ways of representing a graph. Do you remember those words? / can you read them off the board? Everyone's eyes cut to the side. Yes, there's the adjacency matrix, which we're not going to use. There's the edge list, which we're not going to use. And there's the adjacency list, which is to say, which we're not going to use. So as I have this set up, if I have a list of nodes, you remember every node has a list of its neighbors right here. Hang on, I've got 2, sorry. I had 2 different files open. Okay, this is where we are. The graph itself is really just a list of nodes because the way I have it structured, every node has a list of its neighbors. Does that make sense? So that is equivalent to this adjacency list because I have a list of node objects, and node objects are a list of other nodes, contain a list of other nodes. Yeah? So when I instantiate a new undirected, unweighted graph, I just need to instantiate a new list of nodes. And to make this more useful and reusable, actually, I don't know why I didn't do this. I'm going to within my Lab 4 folder, create a new folder called Graphs. And actually, I don't know why this wasn't in the directory. I'm sorry. Oh, that's that. I've got some pre-made graphs that that follow a specific format. Let me see if I'm going to come in here and create a new file, and I'm going to call it graph1.txt. Graph1.txt, okay? And I'm going to copy this. Okay, here is our graph format. Any line that starts with a hashtag is a comment. So this isn't necessary, but I'm documenting what I'm doing here. So these are the names of the nodes in the graph. And I'm going to say here, these are space separated. Any set of spaces. This, on one line, these are all of the names of the nodes in the graph. You with me? Next, I need to put in the edges. I'm going to put in the edges, and I'm going to say AB is an edge, BC is an edge, BE is an edge, and BD is an edge. I'm just exactly copying over this over here just so that this is true about it. Okay, so I've listed out 5 nodes in my graph, and I've said that there are these 4 edges. Can you imagine what this would look like if we were drawing this graph? It was A, there's an A, and a B, and a C, and a D, and an E, and A and B are connected. This is undirected, unweighted, so it's just like that. B and C are connected, like that. B and E are connected, and B and D are connected. So this is this little graph in this format. If you were to look at this, you can see I've got 2 graph kinds of properties listed out here. There is one connected component. You see it? Everybody's connected. You can get from anybody to anybody else. And therefore, any 2 nodes are reachable then because there's just one connected component. So I'm noting this because this may be a thing that we want to compute, the number of connecting components and the number of, and reachability. I mean, really everything is reachable from everything else. I would want to test something where the nodes are not direct neighbors to check for reachability. So, I mean, really it's the case that also A and E are also reachable. I mean, A and C, A and D, A and E. Does that make sense? If I were going to test this, I would like to make sure, I mean, certainly A and B are connected because they're direct neighbors. But what about the multi-hop neighbors? And these are the only multi-hops. Does this make sense? So I've got this simple text-based format for my graph because when you test these, you don't want to have to, like, it takes a lot of code to create this graph if you're going to code this. Does that make sense? You'd have to create 5 new nodes and you'd have to add them all. And then for each one of these nodes, you'd have to add an edge for each of these. I will give you these other files. These are files that we've made in the past. But can you see here? Here are the nodes 1, 2, 3, 4, 5, 6, 8, 9, 10. Here are edges between this. There is no 7. Wait, what is 7? Siete? Siete? Poor 7. That makes it more interesting, though. Okay, so that was on, hang on. I blame Sam for this. If you guys know Sam Flowers, he forgot that. So last time I made everybody make up a graph. Notice then the names of our nodes can be whole strings, not just letters. Do you want to make... It looks like at this point, this is basically a long line. That makes, I think, what has happened here. So this is Spanish, Spanish.txt, maybe. And I want 1, 2, 10 to be reachable. Yeah. If you want to copy paste that, you're welcome to. I'll send you these other files. This just makes it so that you can like try out some stuff without having to do the hard work of defining these graphs. You okay with that? So like then I've done the work here, past Keenan in the past, of creating a constructor, undirected, unweighted graph, where you pass in the path to a file that is one of these graph files, and it will read it in line by line, get rid of spaces, ignore any lines that start with hashtag get skipped. You see, you guys know the continue keyword? Continue means skip the rest of the loop and go to the next iteration of the loop. I'm then adding a set of lines to an array or a list of lines. Once I get all my lines in, I make sure that I have some lines. Otherwise, right, if I have less than one line, there was nothing in the file, and that's no good. I'm using regular expressions, which is a pattern matching language. And this is a special syntax in regular expression, regex, which says find any, I'm pretty sure these are white space characters. Hang on. I'm splitting these, I'm splitting this string here by white space. Like that would be spaces or tabs. And getting, so whatever's on the first line are the node names once you split by white space. That make sense? Add all the node names as nodes, and then iterate over all the edges. So here, the rest of the lines in the file, you see here, this is after I've eliminated all the lines that have nothing. The rest of the lines are just those. So for every 2 node names, I want to create an edge between them. So you see this, I'm splitting the line based on white space. This means like 1 or more white space characters. That's what the plus means. I expect there to always be 2 node names. If you don't give me 2 node names, then something's wrong in the format of the file. You with me? So a bunch of this is just error checking. And then finally, when you get to the end, if you have 2 node names, I want to add an edge between the 2 node names. So finally, we get to code something. Are you ready to code? Windows Update's done? Wow. Thank you, Windows. Okay, so this is our first little foray into seeing how the graph class works. So I want to create a public void add edge. And I guess this is not Copilot that's auto-suggesting this, because I thought I turned Copilot off. Annika. Oh no, it says it says enable. That means it's disabled. Okay. Sorry, it has amazing things to contribute, but I want to do it myself. Okay, so when if I'm adding an edge, I'm giving two node names. I'm going to call them node name 1 and node name 2. Let me get rid of that. So keep in mind, I have created node objects. I have a list of nodes, and I created the node objects when I went through this, but I haven't created edges between them. Creating an edge for an undirected, unweighted graph means that I would like to create a new neighbor for each node. So if A is connected to B, then in an undirected graph, B is also connected to A. And both of them should be neighbors of each other. So A should be in the list of B's neighbors, and B should be in the list of A's neighbors. Yeah? Okay, so adding an edge here essentially means I want to say node 1. This isn't going to work yet, but I want to say node 1, which is a node. Well, let me do it this way. I want to say that node 1 is, I want to get the node by name, passing in node 1 name, or node name 1. This function doesn't exist yet, but you see, I passed in the name of the node, and I need the node object associated with that. Would you let me change this to node 1 name? Because I think the 2 modifies the 1 and the 2 modify the node, not the name. In which case, do you think that n should be lowercase or uppercase? I don't know. Okay. I have the name Ocho, and I need to find the correct node object based on its name. You with me? So if I had a function that could take a node name and give me the node object, it would be really helpful to have. So let's write that. So if I hover over this, this is one of the quick fixes. Get node by name does not exist in the current context. I think this is a good use of this little helper utility in VS Code to say, I would like there to be a method like this. I've basically given you enough definition. Make it for me. Generate this method. And to me, what's cool is here, it knows, okay, you're passing in a string, which I just want to call node name. This is its name, get node by name, and it needs to return a node object. And it's cool, I do prefer that to be private because I don't want people outside my class calling this. Naively, you could for each over every node in the list of nodes and then return the one with the matching name. But there's a cool one-liner you can do here, which is you can say var node is equal to nodes.find. There's a find method where you pass in what's called a predicate, which is kind of like a pattern matching, where I want to say the node, I'm making a function kind of inline here. This function is based on one parameter node, and I want to find the node such that the node dot name is equal to the node name that was passed in. And then I want to return that node. I guess if you passed in a name that didn't exist, then it would return null. Bless you. Does this make sense? So this is another just utility method. This isn't really graph algorithms, it's just coding. I'm going to take this and paste it here and say I want to look up node 2, the node object associated with the second node, the second name, like so. Okay, that was a bunch of work that's boring to do the essence of this. Which is to say, in an undirected graph, I want to say node 1 dot neighbors dot add node 2. You seeing this? Every node, I'm populating the list of neighbors with the other node objects. So now I want to say node 2 dot neighbors dot add node 1. All right. If we had a directed graph, we would not do this. If we had a directed graph, we'd just do it one direction. We'd say node 1 is connected to node 2, but not vice versa. This is void, so I don't need to return anything. But for the sake of error checking, I would really like here to say if node 1 equals null or node 2 equals null, if either one of these get node by name doesn't actually return a node object, that means that somebody typed in the wrong name. Like that would be down here. If we say that A is connected to Bobby, who's Bobby? Like there is no Bobby in this world. There's only these 5 node names. Yeah. So we probably should throw a new exception. And I'll put in a little invalid node name. Probably be better to do that. Okay, I don't know which one it is because I didn't check. You're gonna have to figure that out then. It's either node 1 or node 2, or it's either node 1 name or node 2 name. You with me? Okay, that's enough of that. So now we have this add edge, which allows us to read in these graphs so that we can actually have a graph. Okay. All right. You're thirsty for more. All right. Do you notice the basically I have 2 public methods coming down here next. There is, this is where I want to specialize. There is a DFS and a BFS. Okay? So let's look at DFS. Notice I've got this documentation comment here. It probably pops up here, yeah. So this searches the graph in a depth-first manner, creating a dictionary of node to predecessor node links discovered by starting at the given node, and neighbors are visited in alphabetical order. I'm asking that we visit the neighbors in alphabetical order so that there will be consistent, correct DFS orderings. Does that make sense? And here's the data structure that I've defined that we're going to return. So let's make sure this data structure makes sense. This is a dictionary. What's a dictionary? It's a key value data structure where you look up the key and you get the value. What are the data types of this dictionary? Node to node. So I'm calling this predecessor because this says for every node in the graph, who came before you? Who's your predecessor? Is what is in the value. Does that make sense? So I could then, when we're done with the DFS, you see how this represents the DFS traversal? No, DFS, we do have to give a starting node to say start the DFS from here, because that would be different depending on where you start. So this is my data structure that I'm creating by, basically this is how I'm saving the DFS search. So DFS search is like the ACT test. It's redundant. The S does stand for search. Okay, so let's outline what we need to do here. Step one. Step one. We did pass in a starting node object, not a name, so we don't have to look up the name. To do DFS, we need a data structure. It's fundamentally built on a data structure. What data structure is it? A stack. And do we usually write a stack when we do DFS? No, because we implement it in what kind of way? It starts with an R and it rhymes with cursive? Recursive? Yeah? Okay. So do you remember this pattern that we saw for trees? That to do a recursive algorithm, we typically have a non-recursive starting point and then a recursive utility method, helper method that helps. So that's what this DFS visit is. So DFS visit is the recursive one that calls itself. So what we kind of need to do here is set up DFS and then call the recursive method. Okay, so the setup here is what I want to do is I want to make sure that this whole dictionary is initialized such that I have A, B, C, D, E, or whatever my node names are, the actual node objects, and each of them has a null predecessor. So to begin with, I'm going to have a dictionary that has all of the real nodes, as the keys, and the predecessors haven't been found yet. So for each node in nodes, so these are the nodes in the graph, the node objects, I would like to initialize the predecessor. You okay with me calling this pred? It's short for predecessor, not predator. So the predecessor of node is initially empty. We don't know. The other thing that I'm going to do, based on my algorithm here, is going to use the color. And I'm going to say, color all the nodes white. And then as you visit them, they turn gray. When you have fully explored all of the neighbors of the node, then you turn it black. Does that make sense? So I need to here say that the current color of this node is white, which is essentially saying every node is unvisited. Okay? Then I'm going to call the recursive method, which is DFS visit. And DFS visit needs the starting node as the starting place, which was passed in here as a node object, and it needs the predecessor array because it's going to make changes to that array. When this DFS visit is done, the predecessor array will be fully populated. So most of the work, as it were, is going to happen here in DFS visit, but DFS visit is also pretty simple because the recursion handles the progress, the backtracking, and the going. It maps very nicely into recursion. Okay. So let's now jump down into here. We're starting at the starting node. So each time, let's think about what we're going to do. As we get to a node, we're going to color it gray, which means Essentially, this is the node we're currently exploring, and we're going to choose one of its neighbors, and we're going to visit the neighbor. We said specifically that we're going to visit them in alphabetical order. So we need to look at all of our neighbors, sort them in alphabetical order, and then go in that order. But we're not going to visit neighbor 1, neighbor 2, neighbor 3. When we go to neighbor 1, then we're going to visit its neighbors in a depth first search way. Okay. So first step here, I'm going to color the node gray. I'm going to sort the neighbors. So that we visit them in alpha order. And then I'm going to visit every neighbor. And then at the very end, when I'm all the way done, when I have visited every one of my neighbors, I'm going to color the node black. Does that make sense? So white is we're starting, we haven't visited the node. Gray means we're visiting this node, and black means we have visited the node and all its neighbors. When there are no more neighbors to visit, we color it black. So we kind of have 3 states, and that's why a Boolean isn't quite enough, because we need 3 values. Okay, so this node, whatever node we're currently visiting, its color is color.gray. That's how we're keeping up with the state. How do we sort our neighbors? Node.neighbors. Is there a sort? It looks like there's a sort. Sort. Let's make sure this sort's in place. Notice that this sort method does not return something. You see it's void. Sometimes methods return a new copy of the list or the collection changed, but this one actually changes it in place. So I want to confirm that because that's what I'm expecting. How do we visit every neighbor? Well, that's a for each loop. So for each, I'm going to call it var neighbor, little n neighbor, in the current nodes dot neighbors. Hang on, I need a space there. So I'm just iterating over all the neighbors in this current node's list of neighbors. Yeah? What does it mean to visit the neighbor? Well, for one, are we going to visit nodes that have already been visited? Nope. So if they're black, we're not going to visit them because we already finished. If they're gray, what do we want to do? Gray means we're in the middle of visiting. So I don't think that's actually possible. But if it were, we don't want to go there. I don't think it's possible. So we really want to say only if the neighbor's color is white, which means if the neighbor is unvisited, only in the unvisited nodes, then we'd like to visit there. So we essentially want to call DFS visit to the neighbor, and we want to pass in the predecessor dictionary. Before we do that, we do want to do one other thing, which is when we're about to visit another neighbor, what we've just discovered is the predecessor, right? We've said I am the predecessor of whichever neighbor I'm about to go to. So we need to save that. So we need to say that the predecessor of the neighbor, which I can just index like this into a dictionary, is me, the node that you're on in this iteration of DFS visit. So this node is this node that's passed in. So initially this is the starting node, yeah? So the starting node is going to color itself gray. It's going to look at all of its neighbors and sort them alphabetically. That's what this sort's going to do on strings. Actually, that's not true because that feels like an error. It needs to sort them based on the name, not the memory address of the thing. So actually, I don't know if that would work or not. So we really need to, in our node class, make node implement iComparable. You guys remember iComparable in node? And I'm going to quick fix this by implementing the interface. Remember compare to? We did this before, right? So I'm saying if you compare the node ocho to the node siete, then ocho comes before siete because O comes before S. So that might be confusing for that particular example, but we're saying alphabetically is the order of nodes. With compare to, you remember you return a negative number if this one comes before the other one. You return a positive number if this one comes after the other one, and you return a 0 if they come in the same spot. But there's a kind of a trick we can do here, which is we want to do this comparison based on another comparison. So let's just kick the can to it, and I want to return this dot name, got the capital N name, dot compare to, so it's what it's suggesting, the other's name. Does that make sense? So I want to fall back on whatever it means to compare two string names is what it means to compare two nodes. So now that this is comparable, this is the default way to compare two node objects. Now when I'm here and I do my sort, they'll be done based on the names, alphabetically by name. Okay, so I don't know what I got there, but you see, this is what we have to say. Before we visit the node, we got to kind of remember how we got there, which is to say, the predecessor of the neighbor is whichever node I'm on. Yeah? This is who came before this neighbor in our DFS traversal. It's whoever sent me. Right. How do you get out of this loop? You only get out of this loop if you visited all your neighbors. This is recursive, right? Eventually, you'll get to a neighbor. Eventually, you'll get to a node, and all of its neighbors are not white. They will have no unvisited neighbors. Imagine going through that maze, right? Once you get to a place that has no neighbors or all the neighbors have already been visited, then you got to backtrack. All right. So at this point, when you get out of this loop, you've visited all the neighbors. And now we mark it as done by saying this node's color is equal to color dot black. This node has been visited, not equals, one equals. Is that too small? Guys at this end of the table, can y'all read that still? I like being able to fit a little bit more here. So this is DFS, which I think is not that complicated in that we have a non-recursive starting place. Make sure you set up, which is making everything marked as unvisited. Call the recursive method. You've got to pass in where you start and the starting empty predecessor dictionary. And then as we visit, we're going to say whatever node we're on is colored gray. We sort all the neighbors of this node. We go through all the neighbors, so they'll be visiting them in alphabetical order. we check and say, is this neighbor's color white? That is, have we not visited this neighbor before? You could say it's like it goes from visited to discovered to visited. Sorry, from unvisited to discovered to visited. Right before we visit the neighbor that we've discovered, we mark that its predecessor is this node that we're on, and then we visit it. So at this point, you can imagine we go back to the top, to DFS visit, right? It's recursive. Only now node is the neighbor. And the predecessor array knows that for the current node that I'm on, it has a predecessor link going backwards. I mark this current node as gray, sort its neighbors, and then start going through its list of neighbors that haven't been visited before. All the time remembering my backlink before I go there. So the only way to get out of this loop is to fully have visited all the neighbors by marking the node as black and then returning, which then would return to the previous call of DFS visit, return to the previous call, return to the previous call, until you reach the very first one, which would be this one, which means you fully visited everything. And now this array will have been filled up with every node that you can get to from the starting node, or, right, any of those paths. And because we've done them in alphabetical order, there will only be one possible. This will always return the same ordering. Even if there were many DFS paths, we've said, no, you've got to do the alphabetical ordering. So let's imagine for this graph on the board, if we started with A, so everything's white, from A, we look at all of its neighbors, which is just one, which would go to B. We look at all of its neighbors. Its neighbors are E, D, and C, but we're going to sort those alphabetically. So now we have C, E, and D. We begin at this point. At this point, A is gray, B is gray. B would choose one of its neighbors, so going another level D. C is gray. We look at all the neighbors of C, which are none. So now we're done with the loop. Mark C as black, and that would return, because of the recursive stack, to B. Which now, when we return to B, B's in the middle of the loop. The DFS visit call, when it's done, we'll go back to the loop, and then we'll go to D. Mark it as black, go back. Here, mark it as black, go back. This will be done with its loop now, mark it as black, go back here. It's done with all its neighbors, mark it as black. And then we have a predecessor array. I really like what's on this board, but I guess I need to imagine the predecessor array dictionary would have A, B, C, D, E. A has no, if we started at A, it would have no predecessor. The starting node would not have anything. The predecessor of B would be A. Predecessor of C would be B, and likewise all these would be. So this is how the array would look when we're done. You feeling good about that? Questions?
What's in the A box?
This is my representation of null. Yeah, good question. I guess null would have been a better thing to write. Yeah. So that data structure, which is a dictionary, we made it a dictionary so it would be really easy to find the right row for the particular node object. So this is DFS visit and DFS. Okay. I think I want to add something that's not here, but should be here. I would like to be able to say public bool is reachable. and I'd like to pass in two node names. Node name 1, string node 2 name. Sorry. Node 1 name and node 2 name. How would you do this? Detective, so I really want to say, is C reachable from A? Do we have any algorithm that would help us determine reachability? You got a cheat sheet on this? Does anything sound familiar that might help for reachability? You see it, right? We all see it. So the board says that DFS can be used for reachability. What does that mean? I'm going to return false so that the error goes away. I feel better about that. Do you see what I'm asking? How can we use DFS to evaluate reachability, to determine reachability? Could we do that? I'm ready for something like, no, that's impossible. I've told you all the, surely I did. My friend that went to the gas station 20 years ago and said, how do you get to this place? And the gas station attendant said, oh, you can't get there from here. Like that is actually true in graphs. If you had like a little island out there, you just can't get there. If two nodes were reachable, there was some path. Would DFS have found it? Found a path? Yeah. So one way we could do reachability is we could do a DFS search where at every step before we visit the next node, we say, hey, are you the node I'm looking for? So if this was A, let's start with A. If this is B, there's C. Every time we say, hey, are you C? If you're C, then I found a path to you, so we're good. Does that make sense? You still have to keep up with, have we visited this node yet? You know what I mean? To like make your DFS explore, visit in the same way that our algorithm did. Yeah? So if you were going to do this naively, that is, I think maybe this is more efficient. Yeah, it's more efficient, but it's not in your time. You could have an is reachable that starts with the node 1, and you could have a recursive is reachable that does the same coloring of nodes. You with me? If we had the predecessor array that came out of that DFS, could we use that to determine reachability? And if so, what would be our check? You see what she's saying? If you backtrack through the predecessor dictionary, you could determine what the path is from the ending node to the starting node. But it's even better than that. But wait, there's more. Do we care what the path is to do this function is reachable? We do not care what the path is. We're just asking, is there a path? What property of that predecessor dictionary tells us that there is a path? What do you mean by neighbors with reference to this this data structure? This is what we get, right? This is what comes out of DFS. I like what you're saying. This is the key, this is the value, and really the predecessor of this node is this node. Let me throw one more thing in. Let's imagine that our graph also had a node F, and F has no neighbors. It's not connected to anything. It's a part of this graph. Like, this is mathematically true. This whole thing is the graph. So it would need to be here in the keys because it's a number. What value would it have here? Null. It would definitely, it would start as null because we made everything null. Can I make this null still? Would this null value ever change when we ran our DFS? Starting at, I'm assuming we're starting at A. It is essential that we know where we started from. Would that null ever change? No, there's no way for it to change because we like never visited it. And once we started here, we just fully explored and the DFS ends when we have gone everywhere we can get to from A. So I believe if we have DFS done correctly, we could just call DFS and then check. Call DFS from the starting node, which in our case, is that node 1 or node 2? Answer is, doesn't matter. You could do it either way. You could say node 1 is the starting node, and node 2 is the ending node. If we start our DFS, so if we want to say is reachable, AF, that would be, these are the names of it. We do a DFS starting at A. Afterward, we get back this predecessor dictionary. I think we can just look at this one row and figure out, is it reachable or not? You with me? So you want to try that? So let's say var pred is equal to, oh, hang on, we got to do a little bit of work first. You remember this whole thing? Node 1 is, we got to convert node names to node objects. Does that make sense? This kind of, we've got a map between the string name and the actual object because we'd rather have the actual objects because if we have objects, we can do all the stuff we can do with objects. All right, so now we run a DFS. DFS. How does DFS work? I give it a starting node. That's all I give it. Okay, so you can go either direction because this is an undirected graph. If this were a directed graph, we'd actually have to have more care, and we would have to say, it would matter if you're saying, can you reach A from F, or can you reach F from A? Those would be two different questions, and we have to kind of define which direction we mean. So I want to say, I want to start at node 1. And now this predecessor array is a dictionary that goes from node to node, and for every value it says who the predecessor is. Yeah? And now we do our check. Let me do it, put a little bit of, well, I guess we should be good and say, if you gave me bad names, then You want to throw an exception or return false? I think we should throw an exception. Oh, look how close it is. That's pretty good. So I guess you could say node 1 name or node 2 name. Do you get these same auto suggest as me? And I need to close that, and I need to close that. Semicolon? It is appropriate to think about how's this going to break if somebody does this wrong. And you know if you're doing this in the real world, somebody will mistype the name of a node. And it might be nice to have a helpful error message exception as opposed to just your program crashed. Deal with it. Okay, so this says one of those is not a valid name. Okay, so once we get our 2, we do a DFS and then say is node 2 let me say was a predecessor for node 2 found. If node 2 has a predecessor, it doesn't matter what it is, then there was some path to get to it, right? So I think here we could return the predecessor of the node 2 does not equal null. Does that seem right? So we're looking up in our dictionary the value for the key of node 2. If it's null, if it's not null, then we return true. If it is null, we return false. And I think that's what this logic would do. It's fun, right? Okay. Okay, I want to set.
What if they just go connect though? Because like F could have, like, there could be another node connected to F,
Mm-hmm.
and that could be its predecessor, but it would still not connect to A.
That's true. If we start our search here, we won't ever find G either. So if that's the way we're doing it, F and anything connected to F would have null predecessors in the context of A. Good question, Annika. Thank you. I would like us to take a look at BFS. Do you remember our friend BFS? And this has a similar but just slightly tweaked setup. Notice the data structure that we have for BFS. BFS has a dictionary that we're creating a dictionary. And this dictionary, again, is keyed by node objects. So we're going to have a row in the dictionary for every node object, just like this. But instead of keeping one value, we want to keep 2 values for every node object. We want to keep its predecessor, just like before, but I would also like to keep the distance from the starting node. Does that make sense? So in this example, like if we're going to do a BFS on this little graph, and we want to start at A, then I would have this exact same, actually would have this exact same predecessor, but my value would also include, I'm so sorry, this is underlapping. No, let me just make it. I need 3 things. I've got A, B, C, D, E. I guess now I have F and G too. So I have the predecessor and I have a distance. So the predecessor of A is nothing, and its distance would be 0. B would have a predecessor of A, and it's the one hop neighbor of A. Yeah. C, D, and E are going to be 2 hop neighbors. And these would be zeros, but they would have null. So C, D, and E all connect to B. So for this simple graph, there's only one way to traverse starting from A, right? So if we ran BFS, breadth first search, from A, we would get a dictionary like this. Only now, that's the key, and the value is kind of like, the value is a tuple of predecessor and distance. So that's what that complicated dictionary object is. Yeah, I think you're right. I think that would be a better number. Thank you. So, yeah. The 0 really means you can always get to yourself at a cost of 0. You're starting at 0 when you're doing the BFS. Our initial setup here would be everything's null, everything's infinity. And that means basically we never found a way to you. Thank you, Annika. So I have this results dictionary that is this thing that I want to return. That goes, you see, this is the key node, and the value is a tuple of nodes and distances. Okay. I don't like the way I can't tab over without it auto-suggesting. Okay, I'm going to outline this. I would like to initialize the dictionary. All right, so I need my setup first. And I've already told you the essence of it is all the distances are infinity, all the predecessors are null. But I'm going to go high level here. Next step, I would like to create a data structure that helps me process things in BFS order. What is the data structure that helps me do things in a BFS traversal? A queue. So I want a queue. And I kind of have to set up the queue to be initially empty, and then I'm going to start by adding the first node to the queue. The first node is the starting node. And then kind of my last-ish step is process the graph that is the neighbors of the nodes in the queue. Okay. Okay, initializing the dictionary. I need to create a new row for every node that I have. So I do want to initialize every row. So I need to say my results dictionary at whatever node I'm on. I'm creating this new key. This new row, and I want to say it's a new tuple, and this tuple is the predecessor is null, and the distance is some huge number. Infinity is not something you can assign to an integer, but there is something called int.maxValue, which is the maximum value an integer can hold. Instead of you having to remember it, it's like a constant that's defined on the integer class. So you can say int.maxValue. Does this make sense? This is just setting this up so we have a bunch of nulls and logical infinities. Okay. The other thing that we have to do, remember if we're doing BFS, you don't visit the node again if it's already been visited. So we're going to use our colors for that again. So I would like to say that the starting node's color is equal to gray. And I would like to say that my results dictionary, so basically here let me put a comment. I'm setting up the starting node. If you're going to do the starting node, then you know something. The results dictionary at the starting node is what? What's the predecessor of the starting node? It's null. And what's the distance from the starting node to the starting node? 0. So that's something I know. Okay, now let's create a queue. Luckily, C# has already made queues for us, so I can say queue. I would like a queue of node objects called queue. That's a new queue of nodes. You okay with this? So now I have a queue. What do I do with a queue? I say queue.enqueue, of course. And I want to enqueue the starting node. I'm going to add a word here. We're going to iteratively process this graph. Okay? This is our essence. While the queue.count is greater than 0. So as long as there's something in the queue, then we're going to process it. What does it mean to process this? Let's do this. Let's get the front of the queue, right? We're always going to process this in order. On the first iteration, there's only one thing in it, and it's the starting node. Yeah, so we're going to get the starting node out. We're going to look at all of its neighbors, and we're going to take each of its neighbors and add them to the queue. Yeah? In order to help us keep up with stuff, we're going to say once you get added to the queue, you get turned gray. And once you get removed from the queue, you get turned black, and that marks that you've been fully processed. So the only neighbors that we want to add to the queue are the ones that we haven't seen before, which are marked as white. And actually, we can't trust that. We need to make sure that that's the case. So up here, we should say that node.color is equal to white. That's color.white. You with me? Like, we got to make sure, in case we ran this before, we ran a DFS before, and some of them were, well, all of the reachable ones would have been black. So we'll reset it so everything's white. So now in here, we're going to get the front of the queue. We're going to visit our neighbors. We're going to check our neighbors. And for all of the white neighbors, we're going to enqueue them and update our data structures. Okay. So I'm going to get the node that's at the front of the queue, which is queue. Do I want to dequeue? I think I don't want to actually get it out yet. How do you get it out without, how do you get a copy of it without removing it? Peek. So I'm going to get a copy of that first guy. And then I want to say for each var neighbor, yeah, give me all the neighbors in the current node.list of neighbors. Why did it do that? At a high level, because I know I'm out of time, I kind of want to say queue.enqueue each neighbor. Does this make sense? So each of these neighbors, I'm going to enqueue them, so now they're at the end of the queue. There's some more stuff I need to do in here to update my data structures. But when I'm done, I'd kind of like to see the whole picture. When I've actually visited all my neighbors, then I want to dequeue, which means actually get rid of the thing at the front of the queue, and which I'm calling node in this loop, right? This is node, the thing at the front. I want to say that its color is black to mark it as done. So the thing that we haven't done, which I think let me just show you. I'm sorry I'm having to go so fast. I want to be able to say that the results dictionary of this neighbor is equal to, right, who's the predecessor of this guy? It's whatever node you're on, right? Like you came to this neighbor because you're on the current node, and I need to know what's its new distance from the starting node. And its distance is whatever the distance of the node is plus 1. Does that make sense? Because breadth first search is always just add 1 each time you go through. So I would like to say something like distance plus 1, where I have the distance to the current node. What is the distance to the current node? This is awkward, so I'm giving it to you. It's, at least this is one way. It's the results dictionary for the current node. And keep in mind, this is a tuple, right? Results dictionary to the current node. This is a tuple of predecessor and distance. I just want the second part. And that's, oh, seriously? Okay, apparently it does in fact get named, and we can just say .dist. I didn't know that was the case. That is much easier than what I did last year. You seeing this? Oh, this needs a semicolon. Which maybe you'd rather just do this in line right here. Would you rather do that? Or you would do it in multiple steps? You see what I mean? So this is the distance to the current node, and then we got to add 1. You guys got to go. I will see you guys after a while. I want you guys to finish out this, and I'm going to ask you to add like one more method to this. I'll be sending that to you. Thank you, guys.